Hello, welcome to my webinar. I'm Dominik Kunert. I'm Senior Sales Engineer for Analytical Application at Hamamatsu Photonics. And today I want to talk with you about infrared emitters and hopping through technologies. The presentation is structured as follows. We initially consider the question of what is the infrared region, what are vibrational interactions. We look at analytical techniques and typical for IR. Why is infrared not a bad decision for molecule analysis? Then I introduce latest developments about IR emitter, and we are hopping through these technologies and finish the presentation with an overview and a general comparison. But first, a few introductory words about the company Hamamatsu Photonics. Established in 1953, Hamamatsu boasts over 5,000 employees worldwide and generate a net revenue worth $1.3 billion. Today, we can provide our customers more than 15,000 types of products as custom and standard versions. We invest 9% of our revenue in extensive research and development, leading us to the contribution of 3 Nobel Prizes. With 7 manufacturing plants and several central research laboratories, we strive to reveal mysteries, accelerate diagnosis, and improve industrial yield for our end customers. We are world leader in manufacturing optoelectronic components, modules, and systems, which we either integrate, adding value to our OEM products, or sell directly to our end customers. We are pushing our effort in light-powered innovation and develop technologies that capture, measure, and generate light through a broad spectral range sensors from deep UV to the far infrared, high performance and stable light sources, customizable products for detectors and emitters, high-resolution, spectral-sensitive cameras. Furthermore, we are engaged to expand our laser portfolio step by step. And last but not least, we are combining photonic integrated systems for imaging technologies, detection, and optimal image processing. But now back to the infrared. The infrared is usually divided into 3 spectral regions: near, mid, and far infrared. The boundaries between the near, mid, and far infrared are not really agreed. Here we focus only on the micrometer range. But how does the molecules interact in the infrared radiation? So theoretically, this schematic Jablonski diagram is widely used for spectroscopy purposes to illustrate the excited states of a molecule and the radiative and non-radiative transitions like quenching that can occur between. S0 is the ground state of the molecule, and by interacting with electromagnetic radiation, the molecules are excited to S1 or S2. You can also see typical timescales about the transition. Fluorescence only occurs with more energy in the visible or in the UV. In the infrared region, the vibrational states happen with less energy. A more deeper and detailed theoretical scheme about concrete energy levels for molecule vibration can be found in the graph about harmonic, anharmonic, or Morse potential graph for diatomic molecules exemplary. But in this context, concrete examples would be going too far. So, simply put, in a vibrational spectroscopy, a molecule has a translational and rotational motion as a whole, while each atom has its own motion. The vibrational modes can be IR active. For a mode to be observed in the IR spectrum, changes must occur in the permanent dipole. This is due to the fact that diatomic molecules like O2 and N2 have own band and no permanent dipole, and therefore one single vibration. However, unsymmetric diatomic molecules do absorb in the IR spectra. Polyatomic molecules undergo more complex vibrations that can be summed or resolved into normal modes of vibration. In the case of a linear molecule such as CO2, symmetric stretching vibrations do not absorb infrared light because the dipole moment does not change, but asymmetric stretching vibrations do absorb infrared light because the dipole moment changes. In this measurement example with a random IR emitter with a certain optical frequency, wavelengths are interacting with the molecules, the relevant vibrational modes are activated, the photon energy are absorbed, the molecules are getting in motion, and the measured wavelengths differs from the wavelengths after the interacting with the molecule. To be a little more concrete now, in the infrared, we can see more accurately on the line strength survey. This line strength survey shows how strongly these molecules absorb infrared light with relevant wavelengths changing the vibrational modes in the molecule. So as an example, the CO2 molecule in pink color absorbs very heavily when it's exposed with 4.3 light. However, if we are looking at methane at orange below 8 micrometers, the absorption band is more torn. So going a little bit further, taking gas sensing as an example, there are plenty of techniques operating optical gas sensing in the near infrared. This is true. However, looking at this line strength survey, you can see if you make the jump to the mid-infrared, the absorption characteristics are 10,000 times stronger at 4.3 microns. But what does this mean? This means generally you achieve higher sensitivity, you can contact lower limited concentration, and at the same time a system will have a lot less pressure on its components, the optics, the electronics involved. So with the right components and a suitable setup, a very precise detection is possible down to PPT concentrations. Basically, in their infrared or vibrational spectroscopy, there are various approaches to gather information from the molecules. Applying dispersive spectroscopy means using a broadband light source, often thermal emitter, with a dispersive element in the front of the sample, basically a dispersive grating or prism with an array or multi-element detector as measuring unit. Very common is also the non-dispersive IR approach, using also a broadband light source, but instead of the dispersive element, a bandpass filter or mono or polychromator is used, targeting only specific wavelengths. The light energy will be measured after interacting the sample region, a single detector. What is getting more and more popular due to the ongoing laser development activities is the tunable laser diode absorption spectroscopy. In this case, you do not need simply put external optics like prism or filters, as a laser can be tuned very precise, below one wave number line width over the absorption band of the molecule. To mention further analytical methods in the IR besides tunable diode laser absorption or non-dispersive IR spectroscopy, in the Fourier transform interferometry spectroscopy, typically a thermal broadband emitter, the light is splitted in two beams by beam splitter in optical interferometer, based on the position information of the movable mirrors, and the optical interference signal changes its intensity. A Fourier transform is performed to calculate the intensity of the light of each wavelength. Differential optical absorption spectroscopy is a method to determine the concentrations and total amounts of atmospheric trace gases from remote sensing measurements of light in various wavelengths. The basic principle used in DOAS is absorption spectroscopy. Light traveling through the atmosphere is partly absorbed by trace constituents along the way, following the Lambert-Baer law of absorption. Further techniques are the photoacoustic spectroscopy based on the photoacoustic effect and others more. Why is infrared a good decision in general? Molecules have vibrational interactions with the IR light, which are very unique and have the spectral fingerprint. Tight absorption bands allow high sensitivity measurements with high resolution down to PPT, ideally with the right components. With non-destructive IR or FTIR and other techniques, you can quantitatively and qualitatively determine certain molecule groups very accurate. Due to partly sharp absorption wavelengths, you can avoid potential sources of interference, no fluorescent signal in the IR. You get large informations, and with newer technologies in the detectors and emitters, bring movement in the market. But now to the main topic, IR sources, hopping through technologies, and here we go. The discharge lamps, xenon flash lamps, are mainly used or known in environmental analysis in the UV. But with a new redesigned process of window glass material with magnesium fluoride, the emission spectra of pure xenon gas can be used in the infrared up to 7.5 micrometers too, and bring the source to a new level, an alternative for UV mid-infrared detection systems. In the latest developments, the focus was on a compact design, easy to operate, powerful light amount, and long lifetime to be also ready for harsh environments. Internal lab experiments for CO2 monitoring at 4.3 microns confirm a good performance of xenon flash lamps. In this setup, we used a 2-watt xenon flash module, compared their performance with a continuous wave 24 wattage globar light source. On the other side, there's a scheme, but the block diagram and the components used for the setup and further information about optical path and filters. In this case, we compared the measured output voltage in blue color and without CO2 flow in red color, and the change of the intensity by CO2 absorption. In the example, the output intensity decreases by 300 millivolt for xenon flash and 100 millivolt for thermal globar light source, which confirms the usage of xenon flash as alternative light source due to the pulse mode of xenon flash lamps with less heat generation and higher output energy by the internal discharge capacity. Before we are coming to our next innovative light source, we need to call to mind the theoretical blackbody radiation spectra versus the wavelengths depending on the body temperature, as this is fundamental for a typical thermal emitter. The key information is that the higher the body temperature, the higher the output of the thermal emitter, and the peak of the output shifts more to the shorter wavelengths. With this background knowledge, I want to introduce the new graphene light source, which is a MEMS-based broadband thermal emitter, in which we take advantage about a constant high emissivity and great thermal characteristics of pure graphene. The emitter can be rapidly heated up to 1000 degrees Celsius with low power consumption. In this graph, up to 12 micrometers recorded with an FTIR engine, you can see the spectrum. And you also see that it's affected by ambient gases like carbon dioxide and water. To achieve this performance, a unique design needs to be realized. In the current design, the graphene structure is integrated in a compact TO package with vacuum sealing. The chip itself consists of 2 electrodes for electrical heating and between the graphene bridge structure for thermal insulation. This structure and the material itself implies the following benefits in comparison to thermal emitters. Extremely high rise and fall time in pulse mode. When we are talking in milliseconds for thermal emitters, the graphene light can work in microseconds. But it's not only limited to pulse mode. The source can be operated in CV mode too. Additionally, the graphene source can be modulated with more than 3000 Hz, resulting in an improved signal-to-noise due to this high-frequency modulation. In real-time experiments, the lifetime is confirmed for several thousand hours of operation without any failure. So, something classic, near-infrared or infrared light-emitting diodes or LEDs are optosemiconductors, converts electrical energy into light energy depending on the material composition, typically from the group 3 or 5 in the periodic system. LEDs typically offers the advantage of low cost, small design, and a long service lifetime compared to other technologies. But the challenge is to increase the amount of light power. Hamamatsu mainly focuses on near-infrared LEDs in the wavelengths range from 1200 nanometers to 1550 nanometers, in which we can find stronger bands for humidity measurements in various application fields as an example. Basically, we provide various packages, standard TO package, others already include lenses to focus the light, others are made from plastic to further lower costs, and for integration automatic processes, we also have SMD versions. Next comes the new high flux LEDs for the mid-infrared. As I mentioned before, generally, the LEDs has been associated with low power, and a lot has been done to address this. The new MIR LEDs are improved at least 1 milliwatt. The milliwatt is the CO2 LED, and 1.9 milliwatt typically for methane at 3.4 microns. Sincerely, there has been an innovation in the material structure which has led to a massive increase in output power. Still low power consumption and still long lifetime if modulated, and the same form factor, and these LEDs are also available in low-cost compact SMD mount package. Again, more power yields, more sensitivity and less stress on optics, calibrations, electronics and noise, etc. Quantum cascade lasers are well known as a high-class light source in the mid-infrared. With its many ultra-thin layers, can be angstrom wide, there is some quantum tunneling effect employed, the cascading process where electrons are driven through this medium and emit specific photons. This specific structure enables to design emission between 4 micrometers and 10 micrometers. Here we are talking about distributed feedback structure, ideally suited to provide longitudinal and transversal single-mode emission at a precise wavelength with an extremely narrow line width, around 1 wave number only, and small tuning range of 0.1 wave number. Integrated lenses allow us to use under good stability without beam alignment of invisible mid-infrared laser. They basically guarantee high output power and mode-hop-free tunability. Furthermore, we are engaged to suppress fringe noise, which improves signal-to-noise ratio in laser spectroscopy. To reduce this interference as much as possible, non-reflecting coatings on the optical components and wedge windows are a must-have. Custom power output, custom wavelength width, and custom wavelengths are generally feasible. From the ultra narrow scanning with 1 wave number to a broader wavelength range over 200 wave numbers, the new wavelength swept pulse quantum cascade laser. This broadband quantum cascade laser, based on dual upper state active area, can scan over a broad spectral range by its external cavity configuration with its MEMS integrated mirror, with a spectral line width of only 2 wave numbers with a really fast speed. In a setup with this laser and a Hamamatsu photodetector, the measurements resist of 40 micrometers thickness polystyrene are not quite so bad compared to FTIR. But what are the strengths of quantum cascade lasers? Surely the high output power, which can be achieved in the cascade structure. Secondly, basically it's a laser and not a dispersive source. Then the distributed feedback structure allows ultra-thin line width to achieve extremely low detection limit. Contrary, the swept laser technology alternatively allows broader spectral range. Then you can also observe isotopes, maybe carbon or vibrational states more accurately. But the big but is the initial costs are quite higher compared to alternative thermal light sources. To operate the laser, it requires some expertise and accessories to perform high-accurate measurements. And larger current is basically required to keep the laser running. Hopping to the next technology, combining traditional technology with a modern optical semiconductor approach. Energetic Hamamatsu Photonics company released an innovative laser-driven light source technology, uses a laser to directly heat and sustain a xenon plasma to the high temperatures necessary for efficient deep ultraviolet up to infrared production, up to around 2.4 micrometers. In traditional approaches, such as arc or deuterium lamps, the brightness and the lamp lifetime are limited by the continuous use of the electrodes to couple power to the plasma. The LDLS technology creates a small, high brightness plasma that allows efficient light collection, broad spectral range, and a long lamp lifetime. Nevertheless, high initial costs are one challenge on which we are working, and sometimes nitrogen purging is recommended, and due to high radiance, water cooling is required for some models. In the previous slide, I already highlighted the high power and small spot size. Here you can see a comparison between a xenon arc lamp and an LDLS. The plasma in a xenon arc lamp is spanned from the anode to the cathode, which the most brightness is close to the cathode. Despite barium-impregnated high-resistance cathode, the material degrades after a while, which leads to reduced lifetime, and moving arc point means, in general, instability after a time. In contrast, the electrodes at LDLS are only used for ignition. Then the laser pumps the plasma. The plasma is not pulled out of position and maintain extremely small size, shape, and spatial stability, which makes it more convenient to couple into small fibers or spectrometer slits As this is a very promising and innovative technology, we are now working on wavelengths tunable near-infrared, laser-driven tunable light source, and a mid-infrared version with an upper cutoff wavelengths at 20 micrometers. It's time to come to an end, and I want to finish the presentation with a comparison table between IR technologies without going too deep in detail. As reference, a filament lamp is also listed, which we do not have in our portfolio. Quantum cascade lasers have a very tight output wavelengths. For LED, the output wavelength is wider, but still narrow, and exemplary xenon flash lamps provide a quite broad spectrum. Especially for quantum cascade lasers, xenon flash lamps, and LDLS technology, the light output is comparably high. The unique graphene light source provides fast repetition rates for a thermal emitter with a really small spot size. No one can really beat LEDs in terms of power consumption, and the lifetime is also very long, with several 10,000 of hours ideally. And finally, when we are only looking at initial costs, the LED is maybe closest to the filament sources. So thank you for your attention. If you have any questions or requests, please do not hesitate to contact me. Thank you.